Okay, up to this point, we've done some configurations on routers. You've done IP addresses, you made the interfaces up and down, the shutdown and no shutdown command, put host names on them, looked at CDP, copied the configuration file, know how to copy the iOS to a TFTP server. But we haven't done anything with routing, have we? I mean, the routers themselves, we can now connect to them, telnet, whatever else, CDP, we can see neighbors. You can do a lot of the configurations, descriptions on the interfaces, all labs to do those sorts of things, and to configure IP, and you've configured IP addresses. What we want to do today is start with IP routing, routing the IP packet, sending it from one location to another, getting it to the location that we want to get the information to. Today, we're going to talk about static routing and RIP routing. RIP is a very simple routing protocol, a very busy routing protocol, and not real fast routing protocol. Next time we'll talk about two of the more sophisticated routing protocols, EIGRP and OSPF. But first, and I want to do some demos as we go through this thing. So IP routing itself, getting the packets from point A to point B, from one location to another, from Facebook to you, right? Or from you to Facebook, whichever way you want to go. But generally, you want it to go both ways. If you get the inquiry at the website, you kind of would like the answer to come back. And we'll do most of that stuff with pinging, and yes, I know that that doesn't guarantee that the application's running, but it does guarantee that what we're really concerned with, the routers, is working, that we're sending the IP packet to the location where we want it. So the objectives: understand IP routing, static routing, dynamic routing with RIP and RIP v2, and we'll look at the differences between those two. The time that it takes and how busy they are, and all of the faults that are available in RIP are also available in RIP v2. There is a RIP for IPv6, believe it or not. They call it RIP Next Generation, and nothing changed. So it is a protocol that's there, that's been around, is around, works really well. If you don't want to do a whole lot of work in the configuration, really quick to configure, but also really slow to converge if you've got a large network. If you've got a small network, it works just fine. If you've got a small network, honestly, static routes are going to work probably as well for you as anything else. Problem with static routes, anything changes, you've got to make the changes. If you have a large network, static routes are kind of impractical. For one thing, if you're going to do something to get people to the internet, then you got to put every route on the internet in if you're going to use static routing. It's not really practical. So we'll look at those things. Verify routing. To route, a router needs to know remote networks, neighbor routes, all the possible routes to the remote network, the absolute best route, and on and on and on and on and on. So what we're going to do in this configuration, DCBA, each of these needs to know how to get to the next router, basically, to go into a path. And it goes back to, if we look at a GPS system, how much information does the GPS system show you? Typically. Next turn. If you're reading that thing, it tells you you're going to go so far, and then you're going to get on Interstate 64. You're going to get go straight ahead, or you're going to get off on an exit if you're going to some place. So if you think of a router as doing the same thing as your GPS, that's all they do, except instead of using city names and highways, we use IP addresses, network addresses. Remember, the router is going to find the network. The ARP protocol is going to find the MAC address, the hardware address of the specific host that we're looking for. So we're going to get, and in our case, in this room is a network. And if we didn't have a router going out of here, all of these computers in this room using MAC addressing, since they're all on the same IP network, could talk to each other. We could get information from each other. But if we want to go someplace else, we've got to send it to this other device that knows how to get to other locations. Dynamic routing protocols, static routing protocols are the way that we're going to do that. And when we start talking about these other routing protocols, why do we have so many? Depends on how many routers you have, depending on how fast you want it to be, depending on what the sophistication of the routers is, how much you paid for it, how big the processor, how much memory do you have, those sorts of things are going to factor into that. And when we do the routing protocols, the ones next time, don't think about them as 3 routers. Think about them, I've got 100 routers or 500 routers or 1,000 routers. How am I going to manage that? If you've got 5 routers, 5 subnets, probably static routes are going to work perfectly fine for you. Or RIP will work perfectly fine. RIP's a little bit chatty. We'll get to it. A lot chatty. Sends everything out every 30 seconds. So it has some traffic on it. Basic path selection in this router, in this image here, and these are images out of the book, I think. What a router knows about, and if we look at the center one here, serial 00, fast Ethernet 01, fast Ethernet 02, and fast Ethernet 00, if we went into this router, into the configuration, and used the command show IP route at the enable mode, it would tell us that it knows about all of those interfaces that are directly connected to it. So what a router knows about initially is everything that is connected to it. It's kind of like being in this room. You know everybody that's in the room, but you don't know everybody that's in the building. There has to be some other method to do that. People turn in their attendance sheets, then the registrar gets those attendance sheets, knows everybody that's in the building or everybody that's not in the building. So what these things know about are what are connected to them. They always know about what's connected to them. Now, in order to be connected to them, you need an IP address because it's going to know about a network. So it needs an IP address, and it determines the network address based upon the IP address that's on that interface in the subnet mask. We've said early on in networking too, and we've said on and on and on, subnet mask is used to determine how much of the address is network and how much is host. Well, in this case, it's a really big deal. What's the subnet mask? Because based on the subnet mask, the router is going to know what networks are attached to it. It doesn't know which hosts are attached to it, how many hosts are attached to it, and doesn't really care. All it knows about is the networks. When it finds something that's local, then it will ARP for the MAC address of that specific computer, that specific host, that specific printer, specific whatever it is. If we're going from one location to the other, let's go out here, this one on the left. Let's start out with one of these workstations down here in FA02. They're on the 10.10.30 network, right, with a 24-bit subnet mask, which tells us that the 10.10.30 is the network address. If we went from one of those to a 10.10.10 address, the router would say, hey, I know how to get there because it's attached to me. And it would send it out, interface, fast Ethernet 01. And what we're going to find out is when we do the routes, and these are not really complex commands. Show IP route to show the routes, IP route, network address, subnet mask, either next hop or the interface that you're going out is the command to create routes. And when we do RIP, it's even simpler. So this thing goes up here. It knows about this, ARPs for the address of the specific host on the 10.10.10 network. If it's going any place other than 10.10.40, 10.10.30, 10.10.20, or 10.10.10, it's got to have some other information. So if we sent something to this router and said, hey, we want to go to 192.168.10.12, what's the router going to do? It's going to look in its route table right now, since we haven't done anything, and said, I don't know how to get there. And it's just going to drop the packet. And it's going to send you back an ICMP message that says something clever like network not available, or it doesn't know how to get to that network. So we're not going to go there. If we wanted to, and let's presume this other router that doesn't have any interfaces on it, let's put an interface, an imaginary interface on it, and let's put a network on it. 192.168, what did we do, 10, 16, whatever, address. Then we would tell our router that has everything connected to it, in order to get to that network, go to this router, just like your GPS does. If you're going to go from here to New York City, or from here to Los Angeles, or here to Chicago, or here to any place else, you start out with the first turn. And you have to go through that first turn in order to get there. The same thing happens here. You got to go through that first router. You got to know how to get to that first router. The first router then now has to know how to get to the next router. And we'll look at a couple of hopefully easy to understand examples. Send out the packets to 10, 10, 10, 18. We just did that. 10, 10, 10 is going to go out fast Ethernet 0, 0. And when we do the IP route command, you can either tell it to go to the next hop address. The next hop address is going to be the address on the next router, not the one on your interface, not on the other side of it. It's got to be something that your router can ping, if we want to put it in simpler terms, or actually let's say something that your router is directly connected to, because routers know about things that are directly connected to them. This is the one that, let's do a little demo here, simple IP routing. I've created, I hope, except I use, because I want to use it for both RIP and static, the same one. So instead of using the 172 addresses, all these are 172.16, I used 192.16, and I really confused myself a lot because I had some on 192 and some of them 172. So if we get to that, we'll make the changes. The reason I did that is I want to use this packet tracer demo that I have for both static and RIP dynamic. When we get to RIP, we're going to find out it's a Classful protocol. If I had a 172.16 on all these, then I'd be out of luck, wouldn't I? Because how do you get from 172.16 to 172.16? Can't do it. We have to have different network addresses. So to simplify life for me in this demo, I did the 192.16. Then I typed 192.168 and on and on and on and on and on. So let's see if I can actually find it here. Here we go. So let's go to the first router. Actually, let's look at each of these things to be sure I'm not lying to you. IP config 192.16.2.2. And this router, if we go into here and enable and show IP interface brief, we have 192.16.2.1 on the fast Ethernet, the one that's attached to the switch, that's attached to the computer, and then 192.16.3.1 on the serial interface. 192.16.3.2 should be on the other router. So we'll go to this guy. The show IP interface brief is a really handy command. Tells you a lot of information. I digress. Tells me what the IP address is, the interface, fast Ethernet 00, 192.16.1.1. Okay, yes, method manual status up and up, which tells us that we're good at up to layer 2. Administratively down here means that the interface has a no shutdown command in it. If we're up down means we probably have a problem, not probably, we have a layer 2 issue. Could be a number of things. Could be just be the interface not plugged in. Could be in the serials We don't have a clock rate. Could be, and more in serials than in fast Ethernets, could be that we don't have a compatible encapsulation protocol at layer 2. If we go from Cisco, and I'm going a little bit ahead, but maybe we say this enough, it'll help. In Cisco, the default encapsulation protocol on serial ports is HDLC. Everybody's HDLC is proprietary. So if we connect it to a 3-com router with HDLC, they're not going to work. You have to go back to a standard, and the standard that will work is always PPP, point-to-point protocol. And it's another one, you just have to know how to do these things. None of these commands are very complex. And if you don't know what's there, you type ENCA question mark encapsulation space question mark. It'll tell you what can go after that. Don't be afraid to use the question mark. Use the help screen. Learn how to use the help screen. Learn how to use the tab, because I make, and you probably will also make fewer typos if you use those things. Once you get enough characters to make a unique tab, it'll finish it for you. So use those things. So we have up and up. We have these interfaces, 1.1, 3.2, 3.1 connected to 3.2. And the other computer is connected and has the, well, I guess we might as well look and see, haven't we? Is connected and hopefully has the correct IP address, IP config, 1.2. So I kind of am in the habit of going from left to right. So let's try this thing. We have, this one has a default gateway 192.16.2.1. So can we ping that? If we get into it, maybe we can. Ping 192.16.2.1. And it works. What was the next IP address? Anybody remember? No. Router 0, 3.1. Think we can ping 3.1? Should we be able to ping 3.1? 3.1. Why can we ping 3.1? Let's go back to this router here and do the show IP route. And it says that it knows about 192.16.2.0 and 192.16.3.0. The C over here means that that network is directly connected, C for connected. The other things at the top are kind of these are the abbreviations for the routing protocols. We're not going to use all of them, obviously, but they're all here. Some of the ones that they don't use anymore are still here. IGRP, Cisco doesn't even put that in the new routers, but it still shows up in case you have that protocol on the network. So this guy knows about the 16.2 and the 16.3 network, right? Directly connected. And Jason was right. We should be able to ping that one. We can ping that one because it goes off of the router and comes back to the router. Those networks directly connected. What if I try to now go to the next router to the 13.2 address? Is it going to answer me? What's the guess? 13.1 answered me. Why shouldn't 13.2? As long as it can find 13.2. Oh, let's get back to this guy. 3.2, I said 13. It's 3.2, right? Nothing's happening. Why? I don't have a route. What does that router at 3.2 know about? When I go to this router and use the show IP route command, it knows about the 3 and the 16.1, the 16.3 and the 16.1. But my packet came from the 16.2 network. Doesn't have a route. Somebody said that. Doesn't have any idea what to do with that packet. What if I pinged it from router 0? Would it get back? You don't think so? I bet it does. Why? Both of them know about the 3 network, don't they? Directly connected. Let's see. So router 0, show IP interface brief. So let's ping 192.16.3.2. And lo and behold, we have success. Exclamation points are good. Exclamation points when you copy to TFTP are good. Dots are bad. Dots mean it ain't happening. So since both of these know about the 3 network, they can communicate with each other. They're also directly connected, so it's not a big deal. They are directly connected to each other. So how are we going to fix the situation so that we can do some routing? We have to put routes in, true? That's an obvious answer to why did I ask that question, huh? So let's go to router 0. Actually, let's simplify things a little bit. 192.16.1.0. That's this network, right? Wasn't that the one network? Just so that I can keep things straight. 192.16.3.0. Is that right? This one was the 3, no, the 3 network was in here. Right? And the 192.16.2.0 network was over here. So if I go to this router, trying to show as much of them as I can, in order to change anything, I've got to go into the configuration mode, config T, configure terminal, config whatever, and now I need to tell it how to get to the next network. And the next network that I need to tell it about is which? Covered it up, huh? The 1 network, is that right? 192.16.1? So the command IP route, we're going to give it an IP route to go to 192.16.1.0, and the subnet mask 255.255.255.0, the network that we're trying to go to. And if I had a whole bunch of them, I digress again, what if I had a number of routes that could be supernetted, the word that everybody loves to hate to hear? I could either go in and put 115 or 128 because you got 2, 4, 8, 16, 32. Let's say 32. I could go in and put 32 individual routes or supernetted and have one network, and it would send all of those addresses to the next location. Big advantage to supernetting as we go through these things. You'll sometimes hear in Cisco call it route summarization, excuse me. So route summarization, a number of different terms, but it winds up being supernetting. So what's the next hop address? 192.16.3.1 or 3.2, because I'm on 3.1, right? I could either use the next hop, the address that this router is directly connected to is the next hop address, or I could tell it which interface to go out of. I kind of have always gotten into the habit of telling it what the next hop address is. So if I show IP route now, it says that it knows how to get to 16.1, 16.2, and 16.3. 16.2 and 3 are directly connected. 16.1, the S up here, static route, which means we've told it how to get there. And when we look at administrative distance, which we're going to do in a few minutes, the administrative distance is here in the square brackets. The administrative distance for this guy is 1. It doesn't show up with the directly connected, but the administrative distance for directly connected is 0, and the lower the better in administrative distances. The dynamic routing protocols all have different ones depending upon how dependable they are. Administrative distance is the dependability of the trustworthiness of a particular route. Some of them are going to be preferred over the others. So I can get there. What's the problem if I get there? I guess we could try pinging it again from our workstation, huh? Ping .3.2. I still can't get there. Why not? Can't get back. Routing is a two-way street. So now I need to go to the other router and tell it how to get to the 16.2 network, right? IP, no, that won't work, will it? Config T, I go to configuration mode, route 192.16.2.0.255.255.255.0, and then we're going to go to 192.16.3.1, is that right? And this one now says that it knows how to get to all those different places, 1, 2, and 3. So, with any luck, we should be able to ping that guy this time, shouldn't we? And voila, we can. Routing requires a route in both directions. It's kind of like going to Norfolk and want to come back home. You got to have a route back.
Good luck. It's hell.
It's what?
It's hell, depending on the time of day.
You just got to know the routes to take. You got to know the routes to take. Ah, how we work that in, huh? Are all the routes always busy, even at certain times of the day? And when we get to the more sophisticated routing protocols, they're going to be able to do path determination based on bandwidth, delay, all sorts of things. And Andrew's right. I mean, some times of the day in Tidewater, you don't want to go certain places, like the Virginia Beach Expressway, which they renamed to, what, I-264 or something like that. You don't want to go to Norfolk from Virginia Beach at 8 o'clock, and you don't want to go from Norfolk to Virginia Beach at between 4 and 7 probably. But if you go the other direction, it's not bad, is it? What I always like to do is go to school at Dam Neck when I had to go to a school because I lived in Norfolk. I go from Norfolk to Dam Neck and everybody was jammed up on the other lane. And then when I came home, they were all trying to get back to Virginia Beach and they were jammed up on the other lane still. So
Bumper to bumper.
picking the route can be a big deal. If we use static routes, no picking allowed. That's the way we're going to go. It's like the person may be in Virginia Beach and Norfolk, since we're talking about it, and it does get to be a mess. It only knows one way to get there. Only knows one way to get to the naval station from Virginia Beach, which is the Virginia Beach Expressway. So they go out and sit in the bumper-to-bumper traffic every day. And they only have one way to get home. That's what static routes know. One way. If things get busy, they still know one way. That's the only way that they know how to get from one place to the other. So, say what? Well, it's not always bad because if we're going to our ISP, let's say from this building, how many routes do we have to get to the ISP? One. So why do we want to use the overhead that's involved in a dynamic routing protocol and, oh, by the way, maybe give away some of our network configuration, our network topology, take the risk on that? Why don't we just put a static route in? And there are times that they work out well. There are times that you don't want them. Somebody says if you're an hourly employee and you have a big network, you want to use static routes, right? Because you're going to be busy all the time. But if you're a salaried employee, the network administrator, not so much if you have a large network. If you have a small network, really not that big a deal because you'll have a few routes, not that many routes to do in those particular environments. So there are places for each of these things. The advantage to static routes is they put minimal load, like nothing, on the router. No computation involved. You do all the computation. The other routing protocols do computations. They do the calculations on how to get from one location to the other. This is one, and I think you've seen in the questions, the destination address of the frame will be routing PDU example, host A web browser to the HTTP server. The HTTP server is over here. Host A is going to have in its header information the IP address, the destination IP address of the web browser. How's it going to get there? And he's got a 36-step how routing works. Take a look at it. He goes into infinite detail. But if this guy, host A, is going to the HTTP server, which is across two routers, it's going to first do the ANDing with the IP address to determine if it's local or remote. And it's going to determine that it is remote, we hope. If it had determined that it was local, it would just simply ARP for the MAC address of that host and send the packet directly there. But since it's remote, it looks into its configuration and says, oh, I have a default gateway. So it then ARPs for the MAC address of the default gateway, Ethernet 0 on lab A, and sends the packet with the source IP of host A, whatever it is, and the destination IP of HTTP server, a source MAC address of host A, and a destination MAC address of Ethernet 0. When it gets to the router looks in the packet local or remote, and we hope it makes the determination that it's remote and it has route tables in it. Looks in the route table, how do I get to this destination IP address? It doesn't change the IP addressing. We'll get into NAT later on, actually in the next block, and we'll learn how to NAT. NAT changes the IP address, the source IP address. This is just routing so that the source and destination IP addresses never change. But it's going to say, how do I get there? It's got a route that says go to serial 1, whatever the IP address is. It's going to ARP for the MAC address of serial 1. The source MAC address, in this case, will be serial 0 on lab A. The destination MAC address, serial 1 on lab B. Sends it to lab B. Lab B says, oh, I'll do the ANDing, and golly, you know what? The destination IP address is local, and it's local to my Ethernet 0 interface. So it will then ARP for the MAC address of the HTTP server, send the web query to it. It will then reverse the IP addresses because we're going to send it back to the original source. Sends it back, and it does all the MAC checking as it goes back. And hopefully the ARP table will still have some of this stuff so it won't have to go through all the ARPing all the time. Unidirectional, we've already looked at that, unidirectional, and when you do these things, Cisco always talks about the man in the router. What you do is, and what Jeremy Char says he does is when he does routing is he puts his arms out like he's the interfaces and puts the addresses on them so you know what's going on. And when you start doing access control lists, that may sound silly, but it's a good way to look at that thing, to look at those. Is the packet going in or out? What's it doing with it? But they must be unidirectional. We tell it how to get from S0, or we tell it how to get from 172 from router A to router B, the addresses like we did in the little example, but then we also tell it have to tell it how to get back. The other thing that we may have, and this is the static route commands, IP route, which we looked at, IP route, the remote network, the mask, the address of the next hop. The distance, you can put a metric in here of the number of hops away if you want. It's not a requirement. You can put that in. So router, IP route, remote network, mask, and then the next hop. Those are the only things that are actually required in the command. Static route example, let's see, we just did that one. Default routes are one of the things that I didn't do, and I didn't have my third router here. The default route is something that we would do from here to our ISP. Because if you're going to the internet, how many ways do you have to get there? How many destination networks do you have on the internet? I don't have a clue.
I can't count.
I probably can't count that high either. I'm sure I can't count that high. How many do we have? A lot. Do you have time to sit down and type in all those routes?
No.
Even if you use SuperNet.
Not today.
So we have this really cool command. It's called a default route, IP route 0.0.0.0 for the network address, 0.0.0.0 for the subnet mask, which says any network and any subnet mask, which is all this says is 0.0.0 with a 0.0.0, any network. And we're going to send it to the next hop. From here, we would send it to our ISP, and I don't know the IP address. IP route 0.0.0, subnet mask 0.0.0, next hop address, or we could tell it which interface to go out of. S00 it sends everything out of 0.0.0. And if you look at this thing, if it sends it out of 0.0, how many places can it get to? Can get to the next one. It can get to 0.0 on router B. So if we go out 0.0, that's why you can use either the next hop address or tell it which interface to go out of. Either of those works. He says that he likes to do both, and you can do both as we go through these things. So the IP route command with all the zeros are the default route. Now, the default route will take effect unless we have a more specific route. So if I went back to one of those routers that I just configured and put a default route in it, IP route 0.0.0.0.0, and a different address, it would send everything except my 192.16, and if I'm on the far left router, that went to, what, the 2 network, 3 network, 1 network. It went to the 1 network. It would send everything except the traffic destined to the 192.16.1 network up the default route, because that's the only one that's more specific. More specific means that we actually put in a network address, 172.16, 192.168, 10.12.6.0, whatever network address we put in, that's going to be more specific. The longer the subnet mask, the more specific the route. And you'll get into some questions that they'll have a number of different routes that go to a network. We might have something that's masked as a Class B and something that's masked as a Class C. The more specific would be the one that's masked as a Class C. That's the route it's going to take. So it always takes the more specific routes. Routing versus routed. Let's do this, and then we'll take a break before we talk about RIP. Routing protocols are used between routers to determine the path the packet should take and maintain routing tables. Examples are RIP v1, RIP v2, version 1, version 2, EIGRP, and OSPF are the ones we're going to talk about. There are some other. IGRP is an old protocol. ISIS is a protocol. Cisco doesn't do it in CCNA or in CCNP. Routed protocols are assigned to an interface. They're represent an actual resource, IP address. Other routed protocols, IPX is a routed protocol. It's really not used anymore, but it is a routed protocol. The routed protocol that we're concerned with today is IP. It's the one that we use, the protocol of the internet. Routing protocols, interior gateway protocols, RIP, IGRP, EIGRP, OSPF, an autonomous system collection of networks under a common administrative domain. We have interior gateway routing protocols and exterior gateway routing protocols. He says here BGP. BGP, Border Gateway Protocol, is the protocol that the internet actually runs on. It's the one that shares the route information that is given by the ISPs, how you get to the different networks. It has a huge route table, as you might expect. It has a route table of the internet. You don't have to download it all if you're an ISP. It's also a very slow protocol, slow to converge on purpose. And if you think about it, how many different routers on the internet do you think go down in any, I don't know, maybe 1 second period? If we had instantaneous convergence, the only thing we'd be trying to do is converge the route table, get the route tables up to date. BGP is slow, and it's slow on purpose. It connects interior gateway protocols together. And we're going to talk about autonomous systems. We're going to talk about autonomous systems in EIGRP, but we have autonomous systems in BGP. Autonomous systems, maybe Cox cable would be an autonomous system. So autonomous systems use interior gateway protocols to share routes, and we're going to say we got more than 4 routers. You know, we got, I don't know, 800,000-900,000 routers. You're probably not going to want to sit down and type routes. And then if you change something, then you got to go back and change everything. So in that case, static's not really practical. BGPs connect together the autonomous systems, border gateway protocol, EGPs, exterior gateway protocols, and they have autonomous systems. And these autonomous systems, we have public autonomous systems and private autonomous systems, just like we do with private IP addresses and public IP addresses. If you wanted to have inside your own large network different autonomous systems that are then connected together, you could use BGP to do that without using a public autonomous system. EGPs are connected together. Routing protocols, obviously I got this one someplace else. We'll do this and then we'll take a break. We have 3 different types of routing protocols. Distance vector, which we're going to talk about today, distance vector is RIP. RIP and IGRP, again, IGRP is something that's not used anymore. And the pictures over here, this is the author of this slide's Rabbit Diesel, which doesn't have a whole lot of features. You know, it's got kind of like a 4-speed transmission, seats, maybe an AM radio, and that's it. And then we have link state protocols, and the distance vector, easy to configure. When we get to RIP, it's really tough. Router RIP, and then put the network address in. And since it's a Classful protocol, we don't have to worry about the subnet mask. All we got to do is tell it which networks are connected that we want everybody else to know about. Not many features, RIP and IGRP. Link state, more difficult. He says difficult. It will say a little bit more difficult to configure, more knowledge required. Featurific, lots of features in the Dodge Viper. It's going to be quicker for everything. The examples of those, OSPF, ISIS. And then we have hybrid. Hybrids take the best of both worlds. And a hybrid uses some features of distance vector, some features of link state. The problem with them is they're proprietary. EIGRP is the one that we're going to configure. EIGRP is a Cisco proprietary protocol. It's a very good protocol, but you can only use it if you have a Cisco environment. Are there questions to this point? Let's take a break here for a few minutes. Classful routing protocols, they're between Classful and Classless. Classful don't include the subnet mask with the router advertisement. Within the same network, consistency of the subnet masks is assumed, so that if we're on this network, we assume that everybody in this network has got a 24-bit mask because that's the way that they're masked in the building. Summary routes are exchanged between foreign networks. Summary routes mean that if I did a 192.168.1.0 and subnetted it with a 28-bit mask, then the router would automatically summarize all those routes as a classful network. It's kind of odd in that you can subnet, the router knows about the subnet, but the routing protocol doesn't know about the subnet. So if I had different interfaces and I had different subnets on each of those interfaces, it would be okay as long as as they were all on the same router when we sent those things. Classful routing protocols, RIP v1 and IGRP. Again, IGRP you're not going to see, I don't think, unless you get some really old routers. RIP, the routing protocol, and these you can tell the ones I got from different locations because they have the really cool red background, but the algorithm was first developed in 1969, so it's been around a long time. Comes in two versions, V1 and V2. RIP V1's classful, no authentication, uses broadcast. RIP V2 is classless, supports variable length subnet masks, so it takes the subnet in the routing protocol packet. Adds authentication and uses multicast. So the differences between RIP V1 and RIP V2. RIP V1, classful, no authentication, is a broadcast protocol. RIP V2 is classless, has authentication. When we say authentication, it adds authentication for the exchange of routing information and uses a multicast address instead of using broadcasts. Classless include the subnet mask and the route advertisement. Classless protocols support variable length subnet masking. Summary routes can be manually controlled within the network. Classless, RIP v2, EIGRP, OSPF, ISIS. The more sophisticated protocols, and then they went back and added it in with RIP. Administrative distances I referred to a little bit earlier. Administrative distance is the trustworthiness of the router. Routers can have more than one routing protocol running on them. They can have multiple routing protocols where they exchange routes. But only the one with the lowest administrative distance is going to be shown. So it may have, in this case, RIP 120, IGRP 100, EIGRP 90, and OSPF 110. If it's got RIP and EIGRP running together, RIP has an administrative distance of 120, EIGRP 90, then the EIGRP route's the only one that will be displayed to you. But you can have, again, more than one protocol running on the router at a time. And if you have more than one protocol, the protocols don't share information with each other. You have to use a command called route redistribution in order to redistribute, for instance, RIP routes into EIGRP. They have different metrics, so each of them is kind of standalone, and you can redistribute statics in there also. Statics by default are not advertised unless we do a route redistribution. A distance vector is how far the vector and in which direction. What these things do is share information, sometimes called routing by rumor. Don't allow the router to know the exact topology of the network, knows how to get to the next network. EIGRP and OSPF are going to have the network topology, so they know about the whole thing. All routers just broadcast their entire routing table, and this is something that is, you get more routers, it's going to take more bandwidth because the routing tables are going to get bigger. They broadcast the entire routing table at specific time intervals. RIP every 30 seconds will do that. This is discovering routes, kind of an example here. We looked at it earlier. Networks or routers know about what when they start up before we do anything to them?
Nothing.
Sure they do. What do they know about? If we did a show IP route, we hadn't put anything on it, what did we get?
The default.
The default. What was the default?
I don't remember.
How about the things that are directly connected to it, just like it shows right here in this table? What do they know about? Only directly connected. So this one, the 2621A, knows about Fast Ethernet 00, 172.16.10 network. This one knows about Ether 0 and Serial 0, 172.16.10, 172.16.20, and on down. The 2501B knows about serial 0, 172.16.20, and these are networks, not IP addresses that it knows about. Ethernet 0, 172.16.30, and it knows about serial 1, 172.16.40. And we go down to 2501C, knows about 2 networks because they're directly connected. So when we start up, they know about only those things that are directly connected. What they'll start doing now when we put RIP on is broadcast the information. The 2621 is going to broadcast to, and how far will the broadcast go? How far did broadcast go? How far did broadcast go? We have to send you guys back to routing, or back to networking. Huh? So how far will a broadcast go? Now, no. What stops broadcasts? What device stops broadcasts? Routers. Routers. So if we broadcast from the 2621, how far is it going to go? All the way to 2501A. Is it going to go any further? Nope, because router stops broadcast. So 2621A broadcasts to 2501A. I know how to get to 172.16.10. 2501A then adds 172.16.10 network to its route table. And instead of over here on the right-hand column, the 0 represents the number of hops, 0 directly connected, adds 1 to it. So it knows how to get to 172.16.10 because it already knew that. When we broadcasted it and it said that, it wouldn't add it to the network. But then it will broadcast to 2501A. I probably should have started. I'll start at the other end. It'll work better because I don't have as many networks. If we use the 2501C, it knows about the 16, the 40, and the 50 networks. 2501B already knows about 40. So when C advertises 40 and 50, it looks and says, I know about 40, I won't add it. I don't know about 50, so I will add 50. And 50 goes out serial 0, and we add 1 to it to say that it's 1 hop away. B then advertises to A all of the information that it has, and then A picks that up. We've got a slide here in a second, and this table's in the book that has all of that information in it so that it eventually builds the table. We go here, the 40, the 10, the 50 is 1 hop away, the 10 from 2501 is 1 hop away, and we get over on router 2501A. The 50 network goes out serial 0, and it's 2 hops away because it is 2 hops away, 2 routers downstream. RIP advertises this information every 30 seconds, so it can take a while before a route gets downstream. If we were advertising the 50 network, which eventually gets to the 2621A, 30 seconds to get it to 2501B, 30 more seconds to get it to 2501A, and then 30 more seconds to get it to 2621. We're talking about a minute and a half before it finds out about that information. What happens if, in the meantime, this route goes down? This guy still thinks he knows how to get there. This will, only got a couple slides in a minute, this router will then inform its neighbor that the route's down, what's called a poison reverse. But when it informs that its route is down, how long is it going to take 2501B to tell its neighbor? Another 30 seconds. And then how long is it going to take 2501 to tell its neighbor? Another 30 seconds. So we're talking a minute and a half when a topology this slow when a network goes down. And then this guy knows that this route's down, but 2621 still thinks that it's up, right? Because it hasn't gotten the updates yet. We haven't been to the minute and a half. What if it then tells all these guys that it knows how to get to the 50 network? And this guy says, oh, this guy knows how to get to the 50 network, so it sends the traffic here. This can cause loops. And that's one of the things that can happen with these things. And what we do to prevent those loops is called split horizon in this case. Split horizon says that you won't send an update back through the interface that you got it from. So 2621A got the 50 network from Ethernet 0, 25018. It won't send that update back, so that these things can go down. The other thing that keeps loops, and when this goes down, we do a poison reverse. RIP, we have defined infinity in RIP, 16. The most hops that you can have in a RIP network is 15. If you get to 16 hops, it's infinity, and it drops at it. You should never see a route in RIP that has a 16 in the hop count. If you do, actually you will, but it won't forward in that because it knows that it is to infinity. And routing loops, a couple of oddities in RIP. And the routing loops we talked about, the updates as we go down. RIP uses as a metric hop count, which means that it would see the T3 and the 56K as equals. Not necessarily a good thing. This is a little bit router loops here, but a little bit, I guess, more realistic. If we had RIP running on all of these routers, RIP would see all of these as equal. Not the most sophisticated protocol. Back to the graphic. It's easy to configure, but not very smart. So what we have done, if we're using RIP on these things, each of them has one hop, right? The 56K through router B, one hop. The T1 through router C, one hop. The T3 through router D, one hop. What you've done, if you put RIP on these things, is change this T3 and this T1 line to 56K connections. So RIP, if we have equal costs, are better. Some of the other ones, the ones we'll talk about on Wednesday, will consider how fast it is, what we're going to do with these things. And this is just another one, a hop count, the T1s. And this one's even better, isn't it? We have a T1, 1, 2 hops, 1 hop 64K. Guess what it's going to pick? 64K, because the metric's better. Only uses hop count regardless of the speed of the line. And that's what this graphic is showing, that if we're going from the computer on the left to the computer on the right, as we go through this thing, it's going to pick the 64K connection because there's one hop, the next router. The T1 has 1, 2, 3 hops. Not going to pick it. It's obviously going to be faster with the T1, but it'll pick the 64K connection. One of the issues with route. The other one is the full route table broadcast every 60 seconds, or every 30 seconds. So not just changes, not just what's attached to it, the entire route table gets broadcast. The larger the route table, the more resources it's going to take in order to send that information. We'll do load balance across 6 equal cost paths. Equal cost if we had 3 or 4 or 5 up to 6 T1 lines that went to the same location, same number of hops. It will balance automatically across that. The default is 4. You'd have to go in and change the number of paths in order to make it 6. RIP v2 supports VLSM and discontiguous networks. Discontiguous networks means that we subnetted something and put one on one side and one on the other side. We're going to have a slide here for you in just a minute. The router RIP, actually let's go through a configuration on router RIP. RIP, again, not a real sophisticated protocol. So let's get our same topology up, and this is the same topology with the same IP addresses that we had before. One of the things to do, I think, in order to start any of these routing protocols is to figure out what's attached. When we type the router RIP command, we're going to tell it which networks we want this router to tell everything else about. You don't have to advertise all of the networks on the router. You pick which ones you want it to advertise. When you put the network command in, it activates the interface for RIP and sends the information. The networks that we will have to advertise are the ones that are between the two routers, because if you don't put it on, RIP will never talk. If we just say, hey, we wanted to advertise the 3 network over on the left, the 2 network over on the left, and not the 3 network between the 2 routers, the 2 routers will never share the RIP information. So the first thing that I like to do is show IP route. And now we know that the 2 and the 3 are connected. And we only got a couple here, not hard to remember, but if you've got multiple interfaces, sub-interfaces, and you've got several different networks here, this should simplify things. So we're going to configuration mode, and we're going to type the command router RIP. And you notice that my line changed to config router. So we're configuring this for the entire router. Router RIP, router configuration mode. The next thing we're going to type, since we're in version 1, is network 192.16.2.0. Since it's a classful protocol and does automatic summarization, we don't need the subnet mask. And as a matter of fact, if we put the question mark here, it just gives me a CR which says carriage returned. So I'll do that. The next one that we're going to advertise is the 3 network. So we're going to advertise the 2 and the 3 network. Show IP route. Should I have anything yet? And I guess the answer to that is no, because we don't have anything talking to us that has RIP on it. We've got to go and configure the next router to do the same thing. And again, I do this one. In case you got to spell config right, huh? That's where the tab key comes in. Network. No, router RIP, right? Router RIP. And now the network command, 192.16.1.0. And the 3.0. The 3, that when we put these on, again, it turns the interfaces on. And voila, we already have a RIP route. That's what the R is for in the route table here. The R says RIPs tell me how to get to 192.16.2 network. And to get there, I go 192.168.3.1. The administrative distance, 120. So about any other protocol will preempt this. The administrative distance for RIP v2 is going to be the same. It's going to be 120. 120/1, the administrative distance 120. How trustworthy is the route? The 1, the metric, is 1 hop away. So when you look at these things, if you've got multiple protocols, only the ones with the best administrative distance are going to show in your table. You can have more than one. We could run other routing protocols on this router, multiple routing protocols. It only shows you the route if you have a network that has multiple protocols to get to the same location. It'll only show you the best route. If we had different networks that we're going to with different routing protocols, we have to redistribute one protocol into the other protocol before it'll advertise it to everybody else. You can also redistribute static routes. Static routes are not shared by default. That's one of the I guess, advantages, disadvantages to it. The advantage is they're not shared because that's a security issue. They're not shared. The other one is if you want them shared, they're not shared unless you redistribute them. So RIP, really a quick little protocol. Well, other things, and back to the picture. Wasn't hard to configure, was it? Not very smart, though. Because we can use, RIP v2, we can use subnet masks, but it's a classful routing protocol. And it broadcasts its routing table, the entire routing table, every 30 seconds. Let's see if we can debug RIP. If it will do something for us, we'll sit here and wait. Debug is, there we go, received an update. Debug is the command that you can see what goes on with individual protocols or on the entire router. If you just debug all, you may overload your router with debugging information. Debug just shows us the communication, and you can see the communication here. Should come up like every 30 seconds, right? Received a V1 update from 192.168.3.1 on serial 00, 192.168.2 in one hop. So it can get there by sending it this in one hop. And then it sent to 255.255.255.255 broadcast on all stations broadcast via fast Ethernet 00. Update carries the networks, the 2 and the 3 network, metrics 2 and 1. Build the update, and this thing will keep going. So if you want to see what's going on your network, debug. The way you turn debug off, usually in Cisco it's the no, this is undebug, or all. Undebug, if I want to make these things go away, all, or undebug all, or we could have done undebug IP RIP. That's just too much to type. If you want to turn it off, just all, because becomes unique. It's the only one that starts with a U. So undebug, debug, undebug. RIP, pretty straightforward configuration. Not a whole lot to that particular routing protocol. And that's what this slide's about, which we have looked at. Every device on the network uses the same subnet mask because it's classful. It uses the classful subnet mask. And back to the one I told you at 170 to 172.16, it used it for all those. If I used RIP 172.16, could I have routed anything? Because everything would be on the same, would have the same subnet mask, would be the same network, with a 172.16 network. RIP v2 allows the use of variable length subnet mask by sending the subnet information with each update. And if you look in the packet header, the RIP v2 has a place for the subnet mask, whereas RIP v1 doesn't. It just says 0. It must be 0. Nothing in it. It's got a version number, and that's it. Distance vector, the same. Administrative distance and the timers, it is the distance vector protocol. The only thing that really changed is, well, the three things changed, which were what? That it had a variable length subnet mask, that it used multicast instead of broadcast, and that you could use authentication. You can authenticate between the routers as you send route updates. So that somebody couldn't plug a router into your network with RIP and just start sending routes to your router. That can, not a real big deal, but can be an issue. The configuration is easy. If you want to change from version 1 to version 2, type version 2. That's it. And it can go, and this stuff can go in any order. Router RIP has to be first, but you can do version 2 first or the network address first. It doesn't really matter. And you notice that the network address, again, we don't type the subnet mask, just the network address. It'll take the subnet mask from the interface. This is a split horizon. I know not in great focus, but loop prevention split horizon. If network 4 sent, if C sent the network update to the left, then B wouldn't send the same information back. They broadcast their entire route table, but if it got it from that interface, it won't send it back to that interface. Prevents routing loops. Route poisoning, and this says a route goes down, that it's the infinite hop count sets the hop count to 16, which becomes infinity in the RIP network. Discontiguous addressing is the last thing, and you notice this thing 192.168.10, 192.168.10.0. These show 24-bit subnet masks. RIP-v1 and IGRP don't advertise subnet masks and therefore can't support discontiguous networks. What this really should have is a subnet mask other than 24 because that's the Classful mask, right? What it's showing is they're going to send the Classful mask. If we subnetted this with a 28-bit mask, then they'd be different networks. Will you agree with that? But since they're discontiguous, the RIP will advertise these things as a 24-bit mask. Now, the other thing that you can do if you want to subnet on the interfaces on an individual router, we can do that. 192.168.10 if we had 3 interfaces with a 28-bit mask on it, or 248, yeah, with a 224 subnet mask. We could do that because all of the 192.168.10s would go here. The router would then know where to send them once it gets there. The issue's not subnetting with these protocols. The issue's with the protocol itself. It won't send, can't distinguish the subnet mask. So you can't use those. OSPF, EIGRP, RIP-v2 can advertise the subnet masks and hence can do discontiguous addressing. The discontiguous addressing is part of subnetted networks on one end and part of the subnetted networks on the other end. The reason that the Classfuls can't is because they don't advertise a subnet mask and they automatically do a summation to the Classful boundary when we go through these things. Passive interface, and we're getting towards the end here, passive interface, if you go into the routing protocol, router RIP, we can set an interface, passive interface, which says that, and this one's showing go to the internet, that we don't want to send the advertisements out that interface. So passive interface, the updates, the gateway to the other router, they'll chat away. The updates won't go out the serial 0, which would go to the interface. One of the ways to use a routing protocol inside your network and not advertise the information to other users, to somebody outside your network, is the passive interface command. And that's just a matter of here, router RIP, configure passive interface, serial 0, passive interface, whichever interface you don't want to participate in, whichever protocol. It's the same command for RIP, for EIGRP, and for OSPF, passive interface command. Verifying RIP, show IP protocols, and show IP route. We've looked at the show IP route. Show IP protocols will show you the protocols that are running on your router. If you've got more than one, it'll show you all the protocols, what they do. I guess we can look at that one real quick since I didn't close that, huh? Show IP protocols, it says that routing protocol is, I know you can't see that from back there, routing protocol is RIP, sending updates every 30 seconds, next due in 22 seconds. So the last one when I typed the command was sent 8 seconds ago. Invalid after 100 seconds, hold down is 180, I think, and flushed after 240. So if it becomes invalid, it's going to be another 60 seconds before it's actually flushed out of the system, out of the route table. Outgoing update filter list if we had none, and we don't. And then the fast Ethernet send and the serial 01 send and receive, and the number there should be the version that we're using. Automatic network summarization is in effect. That means that we're going to summarize to the Classful boundary. Routing for networks, 192.16.2 and 192.16.3. So it's sending information about those two networks. So the show IP protocols command. Again, another one that you can find some information about what's going on your router. And we looked at the debug and the undebug, debug IP rip, on all or you all as we go through those things. So what we looked at here is static routes. And are static routes that difficult to do? No. The trick to static routes is when you get there, you got to get back. So be sure you've got a route in each direction. Trace route becomes kind of a big deal here. Is it easy to make typos? You've seen me make them multiple times. Use the tab key. Don't know what to type? Type the question mark key. You can work your way right down a command by using the help function. RIP, really very easy to configure. Router RIP, and then which networks you want the router to tell all the other all of his router friends about. Takes a long time for RIP to converge because it's a broadcast protocol, broadcast every 60 seconds. It's going to take 60 seconds to get to the next router. Once it gets in that table, 60 seconds to get to the next router, 30 seconds to get to the next router, 30 seconds to get to the next one down the line. So the more RIP routes that we would have in a bus sort of arrangement, the longer it's going to take to converge. It is not a rapid converging protocol. Converging, term that I probably hadn't said what it is. Convergence just means that everything's got the same routes. All the routers have the same information when they are converged. How long does it take to get there? It depends on the routing protocols, and that's what part of the other protocols that we'll talk about on Wednesday are about. What do? They do it faster. They do it a little bit more efficiently. But if we don't have a big network, do we really need them? If we don't have an all Cisco network, then we can't use the hybrid one because it's a Cisco proprietary. Questions? I'll quit and let you do labs. Questions? Going once, going twice.